Welcome to the CFE Media and Technology Education session, Safety Validation in an IIoT Industry 4.0 Smart Manufacturing World. I'm your moderator, Mark T. Hosky with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to understand safety as it relates to industrial automation and motion control, validation, procedures, processes, and best practices. Here's a list of learning objectives. We'll touch on these in today's presentation. Additional resources and downloads are available on the left side of the screen below the session's agenda, along with a copy of the presentation, if you like. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes on this session, click the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. If you're experiencing technical difficulties, please log out and back into the session to continue. You may achieve a continuing education credit by passing the final exam at the end of the session. Here's some information about obtaining approved PDFs for today's session. Today's speaker is Terry Meister, Controls and Robotics Engineering Manager at AMT. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology. Terry Meister is the Control Manager at Applied Manufacturing Technologies Incorporated and leads the Controls and Robotics team for AMT's Automated Systems Group, delivering turnkey automation solutions. His focus on people has allowed him to build a team that ensures all systems from AMT are of the highest standard and meets today's safety standards. A part of every system delivered by AMT, a safety risk assessment is conducted to RIA and the industry standards. His expertise in electrical and pneumatic hardware engineering are a result of 26 years in the industry. As Terry continues his focus on safety, he is the chairman of the AMT Safety Committee and also has been a valuable resource on its technical council, looking at emerging technologies and industry trends. These groups help AMT to continue to develop resources to meet today's and the future needs of industry. Terry, please go ahead.
Today, we'll be discussing three main topics: safety risk assessments, safety validations, and the impact to IIoT and Industry 4.0. So to get us kicked off, first, let's talk about the safety process to begin with. When we want to maximize safety, really we find that there's 5 different categories that people fall into, or companies, if you will. They're complacent, combative, which is not a good thing, competitive, cooperative, or collaborative. What do we mean for a company that does this? Well, the first one, complacent. Really, most or all of the people at that company don't recognize safety as an integral part of the process. And what we can see in today's society, there's very few companies today that would fall into category 1. Most understand safety to a certain extent and understand the need for it. We think of a combative company. Now, they're quick to dismiss or argue that safety is a hindrance. So it's stopping the process. I still have a product to make and I need to out the door quickly. Well, those companies are few and far between as well. Now, competitive. When we look at a company as competitive, they're quick to discount safety within their own process. Now, most companies fall within the 4th or 5th category. The 4th one, cooperative, which is good. These ones understand the need for safety. They may not understand totally how to implement it, but they understand that there is a definite need. And the 5th one, where we all want to be, collaborative. They understand the benefits of safety, and they are in full implementation on their systems and machines. Yes, most of companies that we deal with today or that are out there building systems and machines are going to be 4 or 5. We all want to achieve the safest systems and machines that we can, put them out to the customer. So as we discuss the first part, safety risk assessments, why are they important? We're going to discuss who should be involved in them, the terminology that goes along with risk assessments, the procedure that needs to be followed, and documentation. Now, you're going to hear the word documentation several times today, and we're going to emphasize it because when it comes down to risk assessments, validation, documents are an important key that all of us need to keep in mind. And really, it's the proof that we've done our due diligence to make sure systems are safe. We think about safety not just as a piece of the engineering or a piece of that machinery. We need to think about it as a whole solution in the life cycle of a system or a machine. Here's 5 steps that we put together that we try to follow on all systems that we want to engage in. The first step is the risk assessment. That's going to give us what we need, an understanding of what level we need to protect the operator or someone interacting with that machine from. Then we move into the functional safety. So that's the design phase, when we're designing mechanically, controls-wise, electrically. What functional safety needs to be there? It needs to be discussed in step 2. Step 3, we need to mitigate the risk. There's a risk on many machines and systems. How do we mitigate that so we're keeping people safe? 4th, this is a very important point, but many companies miss it: validation. A lot of companies have the risk assessment, their design, their mitigation. It's very clear. They're intentional about what they do. But when it gets to validating, well, by that time, the system needs to be out the door, and they really don't validate the system. We'll discuss why that's so important further in this presentation. And the 5th is continuous improvement. Safety is growing. All of us are continuing to learn more about safety. It's evolving as we think about how we interact with safety, devices, programming, software. All of these things are evolving. So we want to always wrap up our complete safety cycle with thinking about how we can make improvements on the next event that happens for us, whether it's a system or machine, or how we're involved in it. Really, our goal is all the same, isn't it? If we're here listening to this, we're concerned about sending people home safely every day so that they can live an enjoyable life and that they don't have consequences from what happened at work on a particular day. A lot of people wonder, though, the risk assessment. As we get into the details, you'll see it's an in-depth and it takes time. So why is it so important? Well, this enables us to have a systematic analysis and evaluation of the risk associated with that system over the whole life cycle. Now, when we say whole life cycle, remember, a risk assessment isn't just for an operator. We need to look at the risk associated with a machine or a system, all the way from when we think about building it on our floor, when we're programming it, when it gets to the customer, once demolished. All of those things need to be considered in a risk assessment over the whole life cycle. And it gives us an approach to be able to do that methodically so that we can catch all of the risk. Really, it also allows for an impact on supporting the coworkers. The more that we get workers involved in a risk assessment, the more buy-in that they have. And again, the goal is to send everybody home safe and sound. That risk assessment gives us the first step in being able to make a safe solution. Who should be involved in the risk assessment? Oh my, this is a big debate sometimes, because the more people you get involved, the more money that is spent on it, right? However, the more people you get involved, the more buy-in you have. Sometimes we'll see a designer He's in charge of the risk assessment, but he's the only one involved. Really, that's not the best practice. The best practice is to have anybody that's going to involved in the design or the implementation or anything revolving around that system we want involved. So the integrator, the machine builder, the designers, the end users, even the operators and the maintenance personnel. Wait a second, why would we want the operators and maintenance personnel? They interact with those machines differently. We want their experience to come to the table and the maintenance person say, well, how am I going to interact with that? If I have to work on this piece of equipment, how do I know that I'm kept safe? They're going to bring different viewpoints, giving us that whole scope, helping us with that risk assessment. You can see the value of having all of them involved. When we think about risk assessments, we have standards that help us really give us principles along the way so that it can guide us to building a safe system. Two of those are the RIA R1506-2012. That's for the robots and the robotic systems. And we have ANSI ISO 12100-2012, also that gives us a basis for risk assessments. So those two documents really, if you haven't received them and you don't have them, we encourage you to get them because they're going to give you, again, those principles that you need to base your risk assessment. How do you build it? What principles are used in doing so? Those are going to give you that guidance that you need. When we think of the strategy for our risk assessment and risk reduction, we think of it as 5 different pieces that we need to work through. We see here A through E. First, A, determine the limits of the machinery, which include the intended use and any reasonably foreseeable misuse thereof. That's an important catch, isn't it? If we think of, well, just an operator interacting with it every day, we can protect that. But what about the reasonable foreseeable misuse? Here's an example. If we have a gate switch, and well, what happens then? We have an issue, don't we? Yes, that is the foreseeable misuse of that safety system.
Terry,
Yep.
there was a 10-second spot there where you dropped out. I'm not sure why that happened, but if you want to back up to the beginning of this slide and start again, that would be great.
No problem.
That the last time I stopped a speaker for that, it was just on my end, and it recorded just fine. So this may be for naught, but we don't want a 10-second gap.
No problem. So I quit sharing, sorry. All right. So I'll go back one. Come on.
You're doing great, by the way.
Oh, thanks. Okay, yeah, there we are. Wait a second. There we are. Okay. So when we think of the strategy for a risk assessment and reduction, we have really 5 different ways that we do this as we look through the process. We have A through E on the screen. So when we think about A, determining the limits of the machinery, which include the intended use and any reasonably foreseeable misuse thereof. Now that's an interesting catch, isn't it? When we think about reasonable foreseeable misuse, what does that mean? Well, imagine you have a plant and you have all of the gate switches are the same and they require the old hard key that fits in every single gate switch. Now, if an operator or a maintenance person has one key that can fit every switch around that whole area or a plant, well, really that's reasonable foreseeable misuse of. So we need to protect against that, don't we? It's something that we want to make sure that if someone intended to, they could not easily bypass a safety device. B, identify the hazards and associated hazards situations. That's an important one. We're looking at what are the dangers there. We need to estimate the risk for each identified hazard, what is the risk level? And D, we're evaluating that risk. And then we need to make decisions really based on what we see for the risk reduction. And then E, we're eliminating the hazard and reducing that risk by means of protective measures, given safety fences, safety devices, laser scanners. There's a lot of different safety devices that can do that. So actions A to D, yes, they're really related to the risk assessment, but E we can see is related to the risk reduction. So what does all that mean? This is kind of straight out of the specification of ISO 13849-2. How do we interpret that? Well, in this slide, we see those 6 steps in a little more detail and explanation. The first one, step 1, determining the limits of that system. We need to identify the equipment and really the intended use and possible misuse, reasonably, of that equipment. That seems sensible. We're walking through the process. How does the operator or maintenance person interacting? Step 2, we need to identify those tasks or hazards that may be in event of the situation where they're interacting with that system. Step 3, we need to evaluate and assess the risk. So we look at a task or a hazard in 2, and then we look at the risk that is involved in it. So how badly can a person be injured? In step 4, we want to identify the risk reduction countermeasures that really are going to make a basis for how we protect that operator. In step 5, we mitigate that risk. We put those learning that we had in step 4 into practice and mitigate it with those countermeasures that we decided on. And then step 6, we verify that the risk meets the acceptable level. What does the acceptable level mean? We'll discuss that in just a few moments. But really, this is the life cycle of a risk assessment that we want to keep in mind. And it's good to have this each time we start a system. We want to make sure as we discuss a risk assessment that we're doing each of these steps. It'll help us to get in the habit of being able to think and reason on these principles that we have. These are those 6 principles, again, that we're following. And as we mentioned, who needs to be involved? We see on the right side, resources and input we kind of already discussed. We want the end user, the operators, the maintenance. Understand though, even on an engineering side, we want more than just the mechanical engineer or designer. We want controls input. We want simulation input. We want the programmer. If there's software, we want input from him. All of these can be part of that nice group that we're coming and collaborating on this risk assessment. Now, we also want a knowledgeable safety officer, right? Because really, if we have a lot of people that don't have the experience of safety and just in a room discussing it, they're not going to understand how to apply the mitigation. So we want someone who is an expert in safety that's going to help us get to that next step of providing a safe system. Always keep the tools handy. We mentioned 2 of those specifications, but also understand the specifications do not give you the documentation you need to fill out as you work through a risk assessment. It gives you the principles and standards that you need to create that document out of, or you can purchase software as a risk assessment software as well. But you still need the expert because he's going to help you put the input into that document or that program that gives you the good output that gives you what you need to meet as far as a risk level. And of course, the risk, you want people that are experienced, an experienced operator or experienced maintenance person that can tell you how they interact with that system. All of this wraps up for a wonderful risk assessment in the end, where you know you'll have a safe system going out the door. I work for a robotics company. So we've taken the RIA and built our risk assessment off 1506. We decided to use a task-based risk assessment. And there's some terminology that we want to discuss before we show you the ideas and some paperwork that we've created that'll help you understand the process really that needs to be taken. First, we've mentioned it several times, the task. Yeah, that's a piece of work that's done or undertaken. That's a given, right? The hazard. Now, understand the difference between the hazard and the risk. The hazard is actually the potential source of the harm, or that piece that's going to create physical injury or damage to your health. The severity. Now we need to look at, if we come in contact with that hazard, how badly are we going to get hurt? Are we talking about a pinched finger, or are we talking about a broken bone? Or, of course, the worst thing that anything could happen, death. What about the exposure? This is an estimated incident of the operator being in the presence of that hazard. So we think about an operator may interact with that hazard maybe once a day, maybe a maintenance person once a year. Maybe an operator is interacting with that hazard 60 times a minute. All of this is taken into account when you're looking at your risk assessment. What about the fifth one, avoidance? Now that's our ability to sense and elude the hazard if we're in the situation where we need to. How fast can we look at and react to it? The risk, again, different than the hazard. The risk is a combination of the probability of the occurrence of harm and the severity of harm. And we'll show you how that really details out in a chart we'll discuss soon. And of course, the last one, the functional safety. That's part of the overall safety system or the piece of equipment that we're putting out there for the customer. Yet we may need to make sure that it correctly responds to the inputs that we give it, and it shuts down the proper outputs. It's going to create what we need, a safe environment. So now we're going to discuss some of the documents that we've created that help us walk through a risk assessment. And again, as a company, you'll either need to create the documentation or you'll need to purchase a program that helps you do so. But either way, you need the background knowledge and understanding the principles. So we start with a cover sheet. You think of someone that hasn't seen the risk assessment yet, but understands the idea of the system. They pick up their risk assessment that you've done, and we want them to understand a little bit about the system. So on the cover page, we define the system and the sequence of operations for them. This is not a detailed system overview or a sequence of operations. It's just a simple basis. If they were standing next to the system, they could pull it out, look at it, look at the system, and begin to understand the pieces. That's where the system overview helps as well. Again, not detailed, but if we discuss a robot in the system, we want them to be able to see where the robot should be and see it in the system so they can relate the risk assessment to the physical machine. You'll also run into situations where you need to put down notes, determinations, assumptions that you've made. These are very important because as you work through a risk assessment, there may be questions that come up and assumptions that you've made. Put those down in the risk assessment so the next person that looks at it and reviews it understands what you were thinking when you made a determination. And of course, the last piece, the customer acceptance. This is important because remember, we want to do this as a group. We want buy-in from the customer, from the integrator, from the machine builders. We want buy-in from everybody. So at the end, the customer is responsible to be able to sign off on it and say that they understand the risks associated with the machine and that they feel as well that we have mitigated those risks to an acceptable level. The next piece that we look at is our tasks and our hazards. So as we look at a task, we can think of there's a lot of things how an operator would interact with a machine, but there's also tasks where, take for instance, a robot programmer. He's going to interact with that system. So in that system, how does he know he's safe? How can he make sure of that? What is the hazards? When we look at the hazards, understand that when we look at a hazard, we want to make sure that we're looking at without a safety system. So take for instance, a hazard of a robot. If we put a robot in an empty room without any fencing, and there sits the robot, it's an industrial robot, so it doesn't have any safety as far as collaboration built in. What is the hazard that real robot would really have? Of course, that would be high, and we'll discuss that in a moment. But that's where we need to think of the hazard. Without any safety devices, what would be the hazard of that equipment? Because we're going to mitigate it later, we want to look at the potential hazard and risk. And as we look at the tasks one by one, we walk through. Again, this sounds tedious, but as you build the documentation, they become more, really, you can use them across several machines. You just have the documentation. Take, for instance, the hazards that we have. We have a list of normal hazards that are associated with robotic systems. So we can pick from those hazards which ones apply to each task. So as you build your risk assessment library, really you're going to make it easier on you and the company and all those involved as you build it. Then we move to the evaluation of risk. Now, this chart helps us to understand, looking at the severity, the exposure to the hazard, the avoidance of the hazard, and ends up with helping us understand what our risk level is. So let's take a robot again. I reference robots a lot because that's what I do for a living. But just as an example, take a robot, like we mentioned, in the center of a room. No fencing, no safeties monitoring anything around it. What is the seriousness if you were to walk up to that industrial robot that can run maybe up to 3,000 millimeters a second? Well, I don't think you have to reason too hard to bring it down all the way, not minor, not moderate, but we're in the S3 serious category. You are going to get seriously injured if that's the case. If you run into that road, well, it runs into you, we'll say. So we have a serious hazard. And then we look next at the exposure to that hazard. Well, for a robot without any fencing, anybody can walk up to it. So we definitely would say we're at the E2, the high risk, wouldn't you? That exposure level is high. So now we have S3 at the bottom, E2 high, and then we look at the avoidance. Well, it's not likely that you're going to avoid something moving 3,000 millimeters a second. Yes, so we're going to go with not likely, A2, and that takes us into the risk level high. And actually, if you look at RIA for a robot, yes, you're going to see that the performance level and structure category is a minimum PLD category 3. So we look over at our chart on the right, and we see the high level that we were at as a PL, which is our performance level, is a D, and our structure category or category is a 3. PLD category 3. And that's where robots, a minimum safety standard that they need to protect against. Again, now we've evaluated the risk. Now we know how dangerous that is and what we need to protect it against. So next, now that we know the risk, we need to look at our risk reduction. So we look at the initial risk we mentioned was a high. We're going to look at countermeasures, and then we come off with the remaining risk. So those countermeasures may be a lot of different things. They may be fencing, safety devices, other mitigation risks that we may have. That's going to give us the remaining risk where we want it low or a negligible, so that we know that we've mitigated that risk and that we have a safe system for anybody that's going to interact with it. We'll discuss this a little bit more in a further slide. Data, when it comes to your risk assessment, is essential. So what data is needed when we're looking at a risk assessment? Well, we need to talk about robot safe stopping times. Robot stop times are imperative, because the second you hit an e-stop and that robot gets a stop signal, there's a lot of inertia moving that robot. How long does it take to stop it? Safe distance calculations. You have a light curtain or a safety scanner. Those have times that it takes to react to the input signal of that broken beam. Device response times. Yes, a relay doesn't work instantaneously. Again, we're talking milliseconds, but milliseconds matter when it comes to safety. And then you have your software response time. Software is constantly cycling through, so that takes time to respond. So you need to understand and collect all of that data so that you can have a good risk assessment and make sure that you're mitigating the risk in a safe way. Back to that form that we just mentioned. As we look at the left side, we see that our task, again, and the hazards associated and in valuation on this, we get to a medium, but we want to negate that even to a better, lower risk level. So take example of someone teaching the robot. As we see under the countermeasures, what kind of countermeasures do we do so that we can make sure that their risk is lowered? Well, if a robot is in teach mode, it is limited many times to 250 millimeters a second, which is a safe speed for us to avoid. So that's one thing that we can do. Another one that we can mitigate that risk, a single man operation. We don't want more than a person with that teach pendant inside the cell while he's teaching that robot. A 3-position enable switch. So if you're familiar with robot teach pendants, they have a 3-position. You have to be in the center. So if anything happened, you'd let it go quickly, and that would stop that robot instantly. So these are all things that allow us to lower that risk, those countermeasures, and get a recheck into what level we're actually protecting. So we can negate those with countermeasures down to a low risk. So we do that for every task. We go through every task, look at what the hazard is without any safeties around it, what countermeasures we can use, and what the risk is after we've introduced those countermeasures. Once you're done with all of that, and yes, it's quite a bit, but remember, we're keeping people safe and alive. So once you're done with all of that, you have a nice risk assessment deliverable package. Easy to understand, making sure that you went through every step, and then you get buy-in from everybody. That really helps to have a deliverable for a customer. And also, in case there's any question in the future of how you decided to mitigate risk, you have documentation, like we pointed out in the beginning, that's very important. We want to take everything into account when we're thinking about a risk assessment. Number one is safety. We also understand that we need to preserve the process. We have to have a system that does the process that it's expected to do, but that should never override safety. Profitability. If companies aren't profitable, if we're not profitable, then of course they don't stay in business. But again, that should never override safeties. The budget. We have a budget within we need to build a system in. So are we working within that budget? But what that means is when you're budgeting and estimating, you should include time for a risk assessment. The system complexity. If we make a very complicated safety system, people are going to try to bypass it. Keep your safeties simple is a lesson that we've learned in the past. And schedules. When you're scheduling a system, make sure that you put in the schedule time for a risk assessment. If we don't think ahead about doing these things, it's going to get skipped or it's not going to be done properly. And the last thing we want is a system that is not safe. Really, safety can be implemented effectively and efficiently if we have the right people and resources and skill set to be able to do so. So next, we're going to discuss the safety validation. This is one of those last points that we need to cover, isn't it? Now we've done the risk assessment, we've designed it, we've built it. Now we've done the software. Now we need to validate to make sure that we have met that risk level that we were aiming for and negated all of the higher risk hazards. So we're going to discuss 5 points. The principles behind a safety validation, the plan, the designs, the testing, and of course, the documentation. So a few principles that's in ISO 13849-2 that we need to understand and work within. Here it mentions the validation process shall confirm that the design of the SRP or CS, in other words, the safety related parts of the control system, meet the requirements of the ISO 13849-1. So to meet the requirements of that, we need to make sure several things on our validation. We need to make sure it meets the requirements of the performance level that we mentioned earlier. meet the requirements of the specified category. Remember where those came from? Yeah, those came from the risk assessment that we had done earlier. We need to make sure and measure the control devices and avoidance of systematic failures. If applicable, we have software. Any safety software needs to meet requirements, and we'll talk about those in a little bit. We need the ability to perform a safety function under expected environmental conditions. We need to think ahead of what the environment is that the system is going into. We may be building it in a controlled environment, 70 degrees, low humidity, but what if the end result is a freezer that this system is going into? Are our safety devices and functions able to work at the temperatures or environment that it's going to be put in and then at the end result? We need to consider all these things. This last one is a key. Design the operator interface so the operator is not tempted to act in a hazardous manner, such as defeating the SRP or CS. So if we design a system, like we mentioned, so complex, that operator just scratches his head and he knows he's got a job to get done, well, he's going to try to defeat what safety measures we put in there. We do not want that at all. We want to make sure that it is a safe system when we're done and that he doesn't try to bypass all of the things that we have put in place. So make it simple. Also, the safety validation, more principles that we need to think about in the 13849-2. Yet the validation should be carried out by persons who are independent of the design. Why is that a situation though? Well, think of this. Personally, I grew up hardware engineering at first, and I could do hardware engineering all day, even as I got many years in, and then I would take my final design, hand it off to the checker. And what does the checker do? He finds things on those and notes all over. When you get it back, you're like, I looked at those drawings for weeks now, and I missed that simple little thing that I missed. I can't believe it. Doesn't that happen to all of us? Well, that's why it's imperative that we have someone that's independent of that design take a look at it for us. That second set of eyes really will find those small things that may be very valuable, cause a safety issue, that they can point out to us and fix for us. It just makes sense, doesn't it? The validation consists of applying analysis and executing functional tests that we'll talk about further. Really what that means is we need to have, as highlighted, a validation plan. It's not something that's just the thought at the very end of the system. It needs to be planned out. If a system ends up determining through the risk assessment that it's category 2, 3, or 4, we need to make sure that safety function also includes testing under fault conditions, because that's the difference of the lower categories to category 2, 3, and 4, is catching a single fault failure and reacting to that. So we want to make sure all of those principles are followed when we develop a safety plan, a validation plan for it. Here's an overview from the ISO 13849-2, 2012, of how we can validate. What is the process that we need to walk through? Well, we see here first, of course, when we start, we're developing, like we mentioned, the validation plan. But what's included in that? Well, we need to look at the validation principles that we just discussed. We need to implement those in the plan. We also need to think about the design considerations, the documents, the reference documents that we may have that we need to look at. One of those being the risk assessment when we sit down to create a validation plan. And also we need the faults list, making sure that those critical faults, yes, that we haven't excluded any, that they're actually all part and built into our validation plan. Then comes the analysis. So in an analysis, what we want to do is we want to take several different pieces and analyze them separately. Here's an example. The parts we use are important and imperative to a safety function and safety system. For instance, if we use parts that are not rated by the manufacturer, they have not been tested for safety functions, they have not been rated for a certain category level or PL level, and we use that part in our safety system, we're going to be hard pressed to prove that it is actually a safe system and to validate it. So that's where, if you're doing your analysis and is the analysis sufficient, if it's not, you find a device that is not rated by the manufacturer, you're going to have to do some testing on that device. Save yourself the headaches. Most of the time, if you start down that process, you're going to take that device, throw it out the window, and come back and get a device from a reputable manufacturer that actually has tested it and has all the documentation that you need for your analysis. Use quality equipment from quality manufacturers, trusted ones, known in the safety industry, and it'll save you a huge headache when it comes to your analysis. So now we've done our analysis and we've thought through and made sure all of our parts, our software, all of those things are ready to be taken to the next step of some testing. We want to make sure if we have a certain category level that we're matching up to that. If it's a category 2, 3, or 4, again, we need to be ready to test those safety functions with fault conditions. And then we go to the validation record. Now, remember, documentation, documentation, documentation. We want to make sure we record everything needed for the validation. We don't want someone going out to the floor saying that they did the validation, coming back to us and just telling us, oh, it's all set. No, you want a record. You want to make sure that you have the paperwork to prove it. And once we get to that point, we're doing the testing, all of that's done. Has everything been validated? Perhaps you got out to the floor and there you see a safety device that's not in your validation plan. What do? Just forget it? No. Now you need to go back to the beginning, your analysis. Is that safety device rated? You want to go back through those steps until you make sure everything is covered. Then you can say you're at the end of that validation process. So if the validation can't be completed, you need to make sure you change the designs that are necessary so that you make sure you have a safe system that meets the safety levels that you've decided on your risk assessment. When we're making a plan for our safety validation, we have our goals in mind. We want to describe the requirements that we need to carry out for the validation process. So what does that entail? Well, we need to realize the safety functions and specify them. We need to understand the category and performance levels that we're required to meet and validate that it met it. In the beginning, we want to set out to identify the specific documents that we need. Think about the operational or environmental conditions during the testing and testing at the end user. We want to reference those tests and the standards that need to be applied and who's going to be responsible for carrying out each of these tasks. If we don't put a name to it, odds are it's not going to get done, right? We all know that. We have experience with that. We know someone needs to be responsible and ready to sign off that it's complete so we can be verified that we validated correctly. What information is needed? Well, here's a few things that we need to think about when we're creating the validation. And really, it varies by the technology we use. If we're doing a design and then we order parts, we'll need documents for those parts. We'll need software if we have that. We'll need that software in front of us. We'll need to understand the category and PL level. And then we need to start to validate the related parts. Like we mentioned, the characteristics of it, the drawings, the block diagrams, the circuit diagrams, the functional descriptions, time sequence for switching devices, analysis of relevant faults. All of these things, we need that information when we sit down and are ready to validate a system. Sounds like a lot, but remember, this is safety. We don't want to take a shortcut. For software, when software is used, and it's being used more and more on systems, for the safety side of things, we need to make sure we're validating that as well. This is often something that gets skipped as well, because it's a last thought that people have. They figure if they created the software and they're using good components, well, they just trust that one person that did the software. Is that the best practice? Well, it's probably better to validate that it's right. So we need to make sure that that specification is clear and unambiguous. The person verifying it understands the intent of the software. Again, it needs to state the safety requirements, the performance level that it needs to meet. Need evidence that it meets those requirements. And that may be a second set of eyes looking at that with you, going through it, helping them, catching those points that we may have missed. And of course, detailed testing of that validation of that software as well. For validation, there are tools that can help us tremendously when we're validating. One of the practical aids that we have in evaluating is a software called Systema. And it's a free software tool for assisting and validating the application meets the control standards in ISO 13849-1. And really, this is actually a free software offered by DGUV, a German insurance association. And as we discuss this a little bit more, you'll see the benefits of having validation tools that help us to do so. Here's some of the benefits. Systema allows you to take what risk you're trying to achieve, which is based off the risk assessment, and helps you understand if your devices achieve that and your wiring practices. So it assists with the risk parameters. So it determines and looks at performance levels, the category that you're trying to meet. It takes in the common cause failures of a component, the mean time to failure of components, the diagnostic coverage of components. And now you're probably thinking, if you're not familiar with safety very much, what does all this mean? Basically, a part, let's take a relay, a safety relay. It needs to be tested for all of these different things that we just talked about. How long does it take to fail? How many times can it actuate before it fails? All of that testing is done to make sure that that device is going to react in a safe state. And then they qualify that. And that's where you get some of the levels that that piece of equipment stands up to. Is it rated for PLD category 3? Is it rated for PLE category 4? All that testing is done. So how does Systema help with that? Well, Systema actually allows you to import libraries from manufacturers. So some manufacturers, a lot of them that are reputable, have a Systema library, and all of the information that we see on the screen here is built into that library. So as you work through the Systema process, it actually pulls up this information for you. You don't have to go down a rabbit hole and find it, or find that that product you use isn't tested. Yes, it helps you verify all of that information relatively quickly as you learn to use it. So for any of the reputable manufacturers, there's libraries out there to download. It's going to help you to perform that. And it's also multilingual, industry accepted, so people trust it. If they see a Systema report, usually they trust that that has been validated for all the parts and wiring practices used. So the safety validation we need to test is our next one. We need to produce the test plan, but make sure that our records cover the basis written into the specifications, such as the name of the person carrying out the tests, the environmental conditions, the test procedures, the equipment used, the date of the test, the results of the test. Make sure that the validation is against the systemic failures, and also of course those faults in case it's a category 2, 3, or 4. Documentation is the key. We've created documentation to do this so that every system that leaves, we have documentation proving that we've validated our systems. Here's one just small piece of a validation plan that we've created. You see that the category 3 PLD is what we need that device to meet, and the testing that goes into it. We'll take, for example, a simple push button. Here we have an e-stop. So we've already verified that that e-stop meets the correct category and PL level that that device needs to create the safety function based on the risk assessment. But now we're going to physically test it. Some people think going out and hitting the e-stop on the machine, and if everything stops, you're good. Have you tested the faults? What if one of those wires becomes disconnected? Can you prove that that e-stop is redundant? All of these things need to be taken into the validation plan. And you can see that we actually remove each wire, making sure that that fault is caught, that you can't reset the system. Again, a validation plan is the key. Helps when you get to the floor, make sure that your system is safe. From a software aspect. Now, software, the safety related software is either embedded or application software, but again, it needs to include certain things, the functional behavior, performance criteria. You need to verify that that software measures up to the performance level of the safety function. That goes back to the risk assessment. You need to measure and activities that are taken during the software development to avoid systemic software faults, protecting against it. Now, for a small system, a review or a validation may be as simple as a walkthrough or review of that software on a small, simple system. Again, second set of eyes validating it. But on bigger systems, you're going to need someone to sit down and validate the software functions, the safety blocks. Yes, tearing each one apart, making sure that they react and are written in a way that is safe. So the safety validation, who's needed? Well, you see in the first three here, it's all the same answer. Hardware, software testing. You want, again, a safety engineer that did not work on that project or wrote the software or created the design. You want that second set of eyes. Sometimes people require a third-party validation. That may be required by your customers, but that's not really necessary when it comes to the specification. So is it worth it? Definitely. It does require time and effort, but it's not complicated. As you continue to learn it, use the tools that are available, it will be well worth it when we focus on safety. So how does the safety validation, as a wrap-up, apply to IoT, the Industry 4.0, smart manufacturing? How does all that tie together? Well, as machines get more interface with the cloud, more machines are. At this point, most safety systems are still held on the plant floor directly at that machine and directly with the local PLC controller. But in the future, where does that end up? Well, we can be sure it's going to expand. We need to start thinking and forward thinking about the remote connectivity, the things to consider. Think about safeties. If they're accessible from the cloud, which some devices allow that even today, what precautions are you taking to make sure that someone cannot touch the safeties if they are not on site? Or if it is allowed, how can you prevent any accidents? How can you make sure that safety is handled on both ends of that transaction? Of course, we need to look at cybersecurity, the network protection. Perhaps you don't have an IT expert on site or in your company. It's not wrong to go out and start discussing that with IT experts at a different company to understand the cautions that need to be thought about, cybersecurity that needs to be investigated, ransomware, hacking, all of these things need to be considered the second you plug an Ethernet cable that goes to the internet to a machine or a system. What can you do now though? Well, what's your company culture, like we started with? Are you in the 4 or the 5 of that triangle? Does your company culture already implement the existing specifications that are written? We should be. And if we are, we're going to be ready for that next level. As IoT, as Industry 4.0 continue to be defined and the specifications written for these, we're ready to act. Do your research on edge devices and security devices that interact with the internet. Yes, so we covered 3 points. We've looked at the risk assessment. To have a safe system, a risk assessment is a necessity, and it needs to have the right people involved. To ensure that we have a safe system, a validation is a necessity. And what can we do right now? We need to start implementing the safety and the standards that already are here for us and start forward thinking so that we can be a part and prepared for the Industry 4.0 revolution that is upon us. Thanks, Mark, and we're back to you.
Thanks, Terry. Great information. Now we have some time for questions and answers. Questions were from registrants and from the instructor and moderator of this course. Here are a few reminders about the course while we get ready for answering some additional questions. For a seamless online experience, additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes during the session or the Q&A, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time, and if you're experiencing technical difficulties, please log out and back into the session to continue. Again, achieving continuing education credit may be achieved by passing the final exam at the end of the session. So, Terry, here is the first question. Can industrial safety risk assessments and safety validations be a do-it-yourself project for automation or operations experts with standards in hand, or is it best to have professional help?
Excellent question. Really, when it comes to the safety risk assessments, we want to make sure we have the experience behind us when we start them. So can it be handled as a do-it-yourself? Well, you'll want to make sure you have the experts on hand if you are to start creating that documentation. And many times it's easier to get a third party involved when you're starting the process, because the standards are written for principles and specifications to really guide us. However, the documentation isn't there. So you're going to need some help creating the documentation. And once you've done a couple, got them under your belt, then you should be off and running on your own.
One of your first slides showed a triangle with safety maturity levels. How can we move more toward seeing safety as a benefit? And would working that 5-step safety solution cycle help?
So yes, a lot of companies, like we mentioned, are in the 4 or 5, but in the first 3, if your company's not there yet, we want to encourage them to do so. And working that 5-step process is going to help that. They're going to start to understand safety. Again, we want to impress upon them. The goal is making sure the employees, the people that really trust us, are going home safely at the end of the day.
I've heard that safety needs to be considered as a process, not as an event. So when are changes in a work cell significant enough to warrant a new risk assessment? And how do you know?
Another good question. When you think about the hazards that we talked about, if the process changes to where it introduces any other hazards to a task, you want to reevaluate your risk assessment. So it's best to kind of get the layout and an idea of the whole process and then do the risk assessment before you start the design. But you do have to have the whole aspect really thinking about and covering that as you do your risk assessment.
So there are a lot of devices in industry that have safety sensors built in, collaborative robots, mobile robots, other devices. Maybe management thinks that those sensors and the cost of these investments should be safety enough. How can I convincingly explain otherwise?
When we think about, take example of IMRs that are now becoming more reality for all of us and are in a lot of plants. They have safety built in, like you mentioned, but even the specification for those devices mentions that the second you add something to them, you need to look at it from a risk assessment. And that's the same with a robot or a machine. It may be a safe if it was standing there by itself and you didn't put any attachments on it. The second we add anything to it, we want to make sure that our risk level is maintained so that we have a safe system. So review that as a whole, not just as that one device.
And that gets to a related question, safe devices versus safe systems. Can you expand on that a little bit?
So when we think of a safe device, a safety relay is a safe device. And it's actually, if you look at the terminology, it says it's rated for perhaps PLE category 4, but there's always a catch when it's used properly. So when it's used properly is really where you need to look at. You can take a safety relay, wire it wrong. You can take a safety PLC, program it wrong, and it does not meet your category level or your performance level. So the knowledge behind that, making sure that they're not just a component is safe, but that you have a safe system, making sure that that validation is done, verifying that you use that little part in the right way.
Great, thanks. How much does motion control software programming need to change before the safety system needs to be validated?
Again, it goes back to the process and the hazards thereof. If it's adding a hazard and a task that someone is going to be in, basically in front of a hazard that they could get hurt with, you want to revalidate. You want to look at how that safety software is done. That second set of eyes is going to help with that safety software. But anytime the process changes, we encourage someone to go back and review it, even with motion equipment.
So how much is enough safety training to lower risk to an acceptable level, especially as new hires are coming onto the scene in different functions?
So I like to think of it as you need a safety expert is really where you need to start. And that training goes from that person. We refer to them subject matter experts, SMEs, and you want that to be a safety person. So he's going to be able to teach you that. If you don't have that experience, then it's going to be almost impossible to verify anything. So really the training that's necessary, you want someone that has not only the training from a classroom, but experience means a lot as well. So you want someone that has a well-rounded experience, the classroom training, understanding safety devices, and that never ends though. Even once you become an expert, you're going to continue that safety training because today there's probably a new device out there I didn't know about yesterday. So it's continually training and understanding that safety.
And where can we find the information for the data collection that you mentioned as part of the risk assessment?
So if you use a reputable parts from a manufacturer, they make that very easy to come by because they know you need it to validate. So recommendation is using those reputable manufacturers. If you don't, you're going to have to dig for it and you may or may not find it. So another, as we mentioned, the tools out there help with that because they've taken the libraries and you can import a library. It has a lot of that information for you and helps you with that documentation as well.
And when are validations normally performed?
So we do validations before it leaves our plant, basically at our factory acceptance tests. We do a validation before we have a factory buy-off, if you will, at our facility. But we also do one at the end user. When we're ready, the system is done, safeties are locked down, we do another validation at the site to make sure that when we walk out the door, nothing has changed, no one has added devices, nothing has changed in our safety solution so that we make sure we have a safe system. So we actually do at least 2 of them.
Great information, Terry. Any parting advice?
Continue to keep updated with IoT and Industry 4.0. Things are changing so fast. Devices are edge devices now. There's several companies making them. We're in the process. Like I said, we continue to learn. We're continuing to research these day after day. We're fortunate we have an IT expert on our staff. So me and him are continually talking about how this relates. As you look at a system and a machine, what ports can you open to the internet? What ones should stay shut off and monitored? There's so much to learn. Just continue that process of learning.
Great. Thanks again to Terry Meister, Controls and Robotics Engineering Manager at AMT. I'm Mark Hosky, Content Manager, CFE Media and Technology. Thank you for joining us for this session, Safety Validation in an IIoT Industry 4.0 Smart Manufacturing World.